Let's try to graph another equation, the equation r equals 1 plus cosine theta, and we'll look at some variations on Mathematica. So the first thing I notice, as before, this graph is periodic, so it's enough to sketch the curve for values of theta between 0 and 2 pi, and that's because r of theta equals r of theta plus 2 pi, and the point on the curve corresponding to theta is the same as the point on the curve corresponding to theta plus 2 pi. And again, we pick a few values for theta, and we figure out the corresponding r value, and we plot the resulting points. In this case, we're going to solve for the Cartesian coordinates first, and then plot the points using the Cartesian coordinates. And we pick the angle 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So increasing the angle by pi over 4 as we sweep around from 0 to 2 pi. So of course when theta is 0, r is equal to 1 plus cosine of 0, which is 2. So the polar coordinates when theta is 0 are 2, 0, and these actually coincide with the Cartesian coordinates, which are 2 times cosine theta and 2 times sine theta. When theta is pi over 4, r is 1 plus cosine pi over 4, which is 1 plus 1 over the square root of 2. And this is the square root of 2 plus 1 over the square root of 2. And the Cartesian coordinates are r times cosine theta, r times sine theta. These are both the same. They're the square root of 2 plus 1 over 2 for both x and y. And when theta is pi over 2, the r value is 1 plus cosine theta, which is just 1, and the Cartesian coordinates are x equals r times cosine theta, which is 0, and y equals r times sine theta, which is 1. When we get into the second quadrant with theta equals 3 pi over 4, we see the r value is positive, so we have a point in the second quadrant, and obviously the x value is negative and the y value is positive. And when theta equals pi, we get to the origin, and when theta equals 5 pi over 4, we get an r value which is positive, so we stay in the third quadrant, and the x value is negative and the y value is negative, etc. So when I plot these points, I start at the point on the x-axis 2, 0, and when theta increases to pi over 4, the distance from the origin has decreased somewhat, and when theta is pi over 2, the distance from the origin is 1, so the point on the curve has Cartesian coordinates 0, 1. Now as the angle sweeps around from pi over 2 to pi, the distance from the origin is positive but is decreasing until I get to the point when theta is pi and r equals 0, and I'm simply at the origin with Cartesian coordinates 0, 0. And then as the angle sweeps around from pi to 3 pi over 2, we see that the distance from the origin gradually increases, so that when I get to theta equals 3 pi over 2, the distance from the origin is 1, r is 1, and the corresponding point in Cartesian coordinates is 0, minus 1. And then again, as the angle sweeps from 3 pi over 2 to 2 pi, the distance from the origin gradually increases until I get to 2 pi, where the distance from the origin is 2. And then, of course, as the angle increases, we trace out this curve over and over. So this is a heart-shaped curve, and it's commonly called a cardioid. Now, we've seen that there are a number of equations of circles with polar coordinate. R equals a, there's some fixed value of r, is a circle centered at the origin of radius a. And the equation r equals 2a sine theta traces out a circle of radius a centered at the point r equals a, theta equals pi over 2 on the y-axis. The equation r equals 2a cosine theta is also a circle, and this one has a center on the x-axis at the point A0 and has radius A. So we see here the graph of r equals 4 times cosine theta on the right. 2a equals 4 here, so a equals 2. So this traces out a circle of radius 2 centered at the point on the x-axis where x equals 2. And the circle corresponding to r equals 4 times sine theta is shown here in the middle. It's centered on the y-axis at the point y equals 2, and it has radius 2. And the circle r equals 2 is centered at the origin and has radius 2, and that's shown on the left here.